Hi students, this is Viswanath, chemistry faculty for NEET and IIT exams. In last class, we completed some of the multiple choice questions related to energy of orbitals. See the next one. The maximum probability of finding electron in the dxy orbital is, in the dxy orbital, electron density is present in between x and y axis. So, suitable option is at an angle of 45 degrees from the x and y axis we can find electron density. C. Option C is the answer. At an angle of 45 degrees from x and y axis we can find maximum probability density. So option C is the answer for this question. Next. In main energy level, the orbital with more number of nodal planes will be higher energy. Nodal planes increases, then energy also increases. So option A is the answer. Next, which one of the following atomic orbitals is not directed along the axis? Px along x-axis, dx square y square along x-axis and y-axis, dz square along z-axis. This dxy electron density is present in between x and y axis. So answer is option B. Next, which of the following statements is correct? Say this. Three options are given. An orbital describes the path of an electron in an atom. That is wrong. An orbital is a region where the electron is not located. This is also wrong. An orbital is a function which gives the probability of finding the electron in a given region. This is correct. So option C is the answer. Next. The maximum number of electrons in an atom which can have n plus L value, n plus L equal to 4. In an atom, how many maximum number of electrons having n plus L value equal to 4? Say this, for a 3p orbital, n plus L value 4. 4s orbital, n plus L value 4. 3p orbital means maximum number of electrons 6. 4s orbital, we can arrange maximum 2 electrons. So total number of electrons 8. So with this n plus L value, how many electrons are possible means 8 electrons. Next, the orbital angular momentum of 3p electron is, this is the formula. Orbital angular momentum equal to square root of L into L plus 1 h by 2 pi. P orbital L value 1. Substitute that, we can get this one. Root 2 into h by 2 pi. Option D is the answer. Next. The correct order of penetrating power of 3s, 3p, 3d electrons is, penetrating power means which orbital is more closer to the nucleus, then we can say its penetrating power is more. Here 3s orbital is more closer than 3p, which is more closer than 3d. So correct option is option B. 3s greater than 3p greater than 3d. Next. The correct order of screening effects of SPDF subshells is. So here screening effect means which is more closer to the nucleus, that orbital can show more screening effect on the outer electrons. That's why the screening effect order for these subshells is, see here, S greater than P greater than D greater than F. Option A is the suitable option. Next. Which of the following statements about an electron with ml equal to plus 2 is incorrect? Wrong statement we want. So which of the following statement related to magnetic quantum number? Here ml means magnetic quantum number, value plus 2. See this. ml equal to plus 2 means what about azimuthal quantum number? L value 2. So already we know that L equal to 2 means possible magnetic quantum number values minus 2, minus 1, 0, plus 1, plus 2. L equal to 2. What is the subshell? D orbital. D subshell, D orbital. D orbital shape, double dumbbell shape. That means it is a non-spherical orbital. And D orbital starts from third shell onwards. So it may be 3D or any other higher energy level. 3D, 4D, 5D, like that. 6D. Now see the options. The electron could be in third shell. That is correct. The electron is in non-spherical orbital. That is also correct. D orbital shape double dumbbell. That is a non-spherical orbital. The electron may have magnetic quantum number ms equal to plus half. That is correct. The electron is not in a d orbital. This is wrong. So this is the answer for this question. Incorrect statement. Next. See the next one. So these are questions related to energy of orbitals. Next. Filling of orbitals in an atom. When electrons entering into different orbitals in the atom, we have to follow three rules. First one, Aufbau principle. In the ground state of the atoms, the orbitals are filled in order of their increasing energies. That means first lower energy atomic orbitals occupied by the electrons and then higher energy atomic orbitals occupied by the electrons. That is Aufbau principle. Okay. Say this. The order of increasing energies of various orbitals is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, so on. You may get it out. How can we write these energy order for various atomic orbitals means based on n plus L rule we can find. Calculate n plus L value any orbital. Already we completed this rule. Which orbital having lower n plus L value, it has lower energy. Two different orbitals having same n plus L value means which orbital n value is lower, it has lower energy. So based on this rule also we can decide energy of the atomic orbitals. Next rule, Pauli exclusion principle. See the statement. No two electrons in an atom can have the same set of four quantum numbers. In an atom, if we consider two electrons, those two electrons should be differed at least one quantum number. All the four quantum numbers should not be same. See the example. Four quantum numbers for electrons in 2p orbital in carbon atom. Carbon atomic number 6. Electronic configuration 1s2, 2s2, 2p2. 2p2 means we have to write like this. px, py, pz. For first electron, if we write quantum numbers 2p, principal quantum number 2, azimuthal quantum number 1, magnetic quantum number plus 1. Because L value 1 means magnetic quantum number value minus 1, 0, plus 1. For px orbital, magnetic quantum number plus 1. Already we completed this point. Spin quantum number either plus half or minus half. Suppose plus half. For second electron, quantum numbers n value 2, L value 1, magnetic quantum number minus 1. Py value, magnetic quantum number, py orbital, magnetic quantum number minus 1. Magnetic quantum number minus 1 and spin quantum number plus half. In this way, if we compare quantum numbers for these two electrons, magnetic quantum number is different. Remaining three quantum numbers are same. In this way, no two electrons in an atom should not have all the four quantum numbers are same. They must be differ at least one quantum number. See another example, neon, atomic number 10. Configuration 1s2, 2s2, 2p6. For 2s electrons, if we write quantum numbers, for first electron, n value 2, L value 0, because S subshell, L value 0, magnetic quantum number 0, spin quantum number plus half. For second electron present in the same orbital, n value 2, L equal to 0, M equal to 0, S equal to minus half. Here spin quantum number is different. Remaining quantum numbers are same. Here magnetic quantum number is different. Remaining quantum numbers are same. In this way, in any atom in the periodic table, if we consider any atom of the element, no two electrons should not have same set of four quantum numbers. They must be differ at least one quantum number. Say this, from this we can write this Pauli exclusion principle in another way. Only two electrons may exist in the same orbital and these electrons must have opposite spin. Say this, in this orbital two electrons are there. One electron spin is plus, another one plus half, another electron spin is minus half. Suppose one more electron, third electron is also present in the same orbital. Then what about the spin? Either plus half or minus half. But that is not possible because repulsive forces are dominating if three electrons present in the same orbital. That's why this Pauli exclusion principle we can say in this way also. Only two electrons. we can conclude from this principle this statement: only two electrons may exist in the same orbital and these electrons must have opposite spin. Okay, very important point for multiple choice questions. Remember carefully. Next. See the important useful formula already we completed in the quantum numbers. The maximum number of electrons in the shell with the principal quantum number n is equal to 2n square. Example, n equal to 3. How many maximum number of electrons in this shell? Substitute, then we can get 18. Next, Hund's rule of maximum multiplicity. It is related to degenerate orbitals. Already in the previous topic we completed degenerate orbitals. Orbitals having same energy, those are called degenerate orbitals. Here, pairing of electrons in the orbitals belonging to the same subshell, that those are degenerate orbitals, does not takes place until each orbital belonging to that subshell has got one electron each. That means it is singly occupied. Simple way, see this same statement we can understand in a simple way. In degenerate orbitals, pairing of orbitals takes place after each orbital is occupied by single electron. So in case of degenerate orbitals, each orbital first occupied by one electron and then pairing takes place. Take example, we can understand very easily. Suppose if we take nitrogen atomic number, how much? 7. So this is nitrogen, 1s2, 2s2, 2p3. Okay. Here 2p3. In 2p subshell, how many orbitals are there? How many orbitals? 3 orbitals, 2px, 2py, 2px. In these 3, px having 1 electron, py having 1 electron, pz, 2pz having 1 electron. In this way, all the 3 electrons first enters into px, py, pz. Each orbital can be occupied by single electron. Next, one more electron is there, then only pairing takes place. This is correct. See this, if I write same configuration in another way, then this is wrong. See this is wrong. This type of arrangement is not possible. This type of arrangement only possible. That is Hund's maximum multiplicity. Okay. So these are degenerate orbitals. In this type of degenerate orbitals, all these are each orbital first occupied by single electron and then pairing takes place. That is how Hund's rule of maximum multiplicity. Now see the last topic in this, stability of completely filled and half filled subshells. Completely filled subshells are there or half filled subshells are there. Those elements have extra stability than other elements. What is the reason? Two reasons are there. One is symmetrical distribution of electrons. Say this, electrons in the same subshell, example 3D, have equal energy but a different spatial distribution. 3D subshell having 5 d orbitals, their arrangement is different, but those are having equal energy. Consequently, their shielding of one another is relatively small. All these orbitals having same energy. That's why one electron cannot shield other electron to the greater extent. That shielding is very, very small. And the electrons are more strongly attracted by the nucleus. So because of that symmetrical distribution of electrons in degenerate orbitals, their stability is more. Next, see this one. This is d orbital. Each d orbital having one electron, dxy, dyz, dxz, dx square, y square, dz square. So this electron can shield this electron to very less extent. Shielding is less means those are strongly attracted by the nucleus. That's why their stability is more. So this type of arrangement is called symmetrical distribution of electrons. Next, another reason is exchange energy. The stabilizing effect arises whenever two or more electrons with the same spin are present in the degenerate orbitals. In the degenerate orbitals, two or more electrons having same spin, then it gives more stability. These electrons tend to exchange their positions, and the energy released due to this exchange is called exchange energy. The number of exchanges that can take place is maximum when the subshell is either half filled or completely filled. As a result, the exchange energy is maximum and so is the stability. Say this one, in case of d orbitals, half filled configuration, 1, 2, 3, 4, 5. This first electron can exchange its position with the second one, with third one, with the fourth one, with the fifth one. That means first electron enters into this, third electron enters into this. Otherwise, first electron enters into this, second electron enters into this. Similarly, with the fourth and fifth also, first electron can exchange its position. Due to this exchange, some energy is released, that is called exchange energy. More unpaired electrons or more completely filled electrons are there, more number of exchanges are possible. That means more energy is consumed. Because of this exchange energy, atom stability increases. The stability of the atom is increases. That is the reason. So half-filled configuration like chromium having half-filled configuration and copper also having copper having completely filled configuration. This type of configuration is present in the elements. They have extra stability due to symmetrical distribution of electrons and exchange energy. See the related numerical multiple choice questions. The ion that has different number of electrons in the ultimate and penultimate shells. Here ultimate means last shell, penultimate shell means the shell before the valency shell. So sodium so Na plus ion configuration, K plus Cl minus Ca2 plus. This is valency shell or ultimate shell. 8 electrons are there. Before shell, penultimate shell. In this 2 electrons are there. So 8, 2 both are different. In remaining 3 ions, valency shell and penultimate shell having same number of electrons. So option A is the answer for this question. Next, Aufbau principle failed to explain the configuration of element with atomic number 24, chromium. Say this. This is chromium atomic number. Between 4s and 3d, n plus L value is less for this 4s. So according to Aufbau, it has lower energy, it has higher energy. After filling of this orbital, electron enters into this. But in this case, before completion of filling of this orbital, electron enters into this, because when electron enters into this 3d orbital, this element can achieve half-filled configuration, which gives extra stability for this element. That's why before filling of lower energy orbital, higher energy atomic orbital occupied by the electron. Okay, so option C, 24 atomic number for chromium. Next, if Pauli's exclusion principle is not known, the electronic configuration of lithium atom is. Pauli's means it is related to number of electrons present in the atomic orbital, particular atomic orbital. Maximum 2 electrons we can accommodate. If this principle is not proposed, then in the same orbital there is a possibility to arrange 3 electrons. That means configuration is 1s3. Okay, option C answer. Next, which of the following arrangements of electrons is most likely to be stable? Say this type of arrangement, all are having same type of spin and symmetrical arrangement. So this type of configuration gives more stability for the respective element. Option B is the answer. Okay, so practice well. Atom is very small but chapter is big. Practice well, you can do well in the exams.